Great, and yeah, I think that's a great point about the amount of data that we're projecting or protecting. One of the things that we heard earlier today was that just with the loan amounts and securing, I think it was just home loans, we're securing the equivalent of the GDP of both the USA and China combined. And that was a stat that astounded me earlier today. There have been some great presentations that I want to talk about. Let me turn off my camera so you can see the presentation and not me. I think we've seen a lot of great technology today, and we've seen a lot of interesting ways about how people secure data. But one of the things that what I'd like to point out right now is that one thing that all of those other great technologies had in common is they're using fundamentally the same means of protecting data in flight that we've been using for the last 30 years, right? We have, and that's what we're going to talk about today, is how we secure data in flight. In a little bit more detail, we're going to go through, first of all, what the problems are with securing data in flight. In particular, we're going to talk about in banking and finance, some of the ways that data in flight moves around, and then what the problems are in specific terms, but not overly technical terms, so that really anyone in this call will be able to understand what the vulnerabilities are today. After we do that, we're going to talk about the solution, or our solution to solving that problem. And then we're going to work through some specific use cases that we reviewed earlier on in the presentation to talk about how our technology is being put into use right now in order to protect data in flight. All right, so before we get into the problem, let's talk about what kind of financial data that we're moving around. And there are many of them. I'm not going to cover all of them here, but these are based on our work with financial institutions about where we've identified vulnerabilities in securing data in flight. First of all, obviously with mobile banking, whether it's a mobile application or a web interface, there's a reason your financial institutions, by and large, tell people not to use public Wi-Fi to access their bank accounts or do bankings, right? There are known problems, which we'll be able to get into soon. Those same problems, unfortunately, exist when you're talking about communication between data centers, whether it's an on-premises data center that's managed by that financial institution or multi-cloud data centers. The communication between the services located at those different data centers has to be protected when it goes over the internet, right? And it isn't just the running of the application there, but the connection of the people, who of course do not live in the cloud, to access that data, whether they're availing themselves of those services as the customers were, but from inside the bank, or whether it is bank employees logging in an administrative way to manage what's going on. That's again data in flight that's traversing the internet and needs to be protected. Finally, other organizations, right? No bank is an island, no financial institution is an island. They have to work with each other, whether it's with loan servicers, loan providers, reselling those loans, know your customer providers. All of these other organizations that banks have to deal with and other financial institutions have to deal with require security in that communication, because that's very valuable information that's going back and forth. So that is what type of information we're talking about protecting here in the financial industries. Let's now talk about what the problem is. And first, let me say what is not the problem, and that is encryption. We have great encryption algorithms right now. If you are using NIST-approved algorithms properly, that encryption is really strong. And it's going to be essentially impossible for a bad actor to break it unless they have the key. The problem is that, again, we're not going to get too technical about it, but just like a lock, if you have the key and you can open it, same thing with encryption, right? If I have the cryptographic key, doesn't matter how strong the lock is or the encryption is, I can access that data. So what I'm going to talk about today is specifically about TLS or HTTPS, which is how we're securing most of our communication online today. But it applies more generally to all encryption that we've looked at. But to talk through specifically the HTTPS, the way that it works is you start out with a cryptographic key at one end, okay? That key is used to negotiate a symmetric key that is then used to encrypt the data. Remember, encryption is like a lock. If I have the key, I can encrypt the data. The data is then sent to the receiver, where the receiver decrypts it and then can do whatever it needs to do with it. Okay, we call this secure not because we think the internet is a safe place. In fact, we think the exact opposite. But we keep these keys secret from the bad actor so that the bad actor, even though they can get access perhaps to the data in flight, they can't decrypt it. So we still call it safe. So what's the problem? Well, first of all, the problem starts with this key right here. If the bad actor obtains a copy of that key, the bad actor can not only read that data, but also modify it. So for example, with a money transfer, you can change the intended recipient. What that means is that this key is essentially acting as a single point of failure to the security of this system. But it isn't the only single point of failure. The only reason that the sender trusted that cryptographic key was because it was signed by a certificate authority. And without getting to the math of it, the certificate authority essentially vouches for the authenticity of this key. And senders, or all of our machines, come trusting the certificate authorities that are part of the internet, right? And that's great because we can verify that that key is coming from the receiver, except it also means that the private keys behind each of those certificate authorities also acts as a single point of failure to the security of the communication. And what that means is that if any one of those keys were compromised by a bad actor, again, that data can be modified, it can be read, it's essentially compromised. So more single points of failure. And it isn't just those certificates that are trusted by people's machines. Many of you are already using data loss prevention tools or SSL intercept attacks to filter malware as it's coming into your networks. And while that's important, and I'm not saying anything against that functionality, what it means too is that the private keys that are behind that same malware filtering that's used for good can be used by the bad actor, once again, to compromise this data in flight. Okay, long story short, the way that we secure our data has literally hundreds of single points of failure, any one of which, if compromised, causes this data to be potentially compromised as well. Okay, and that's interesting to me. I worked for a number of years at Cisco Systems in their core router group, and I was in the high availability team. And we remove single points of failure from every part of that core router. But it's not just that, it's every production service that we deliver today. We have redundant power, network connections, databases, load sharing web servers, even redundant geographies when we're streaming movies, for example. Yet when it comes to securing our data, not only do we have one single point of failure, but we literally have hundreds of single points of failure. And we call it a best practice. What in short that leaves us with is a system that is unsecure because of these hundreds of single points of failure. But beyond that, we also have no ability to even know when we're being attacked, because we don't have any control over most of the keys that I just described. And so if they were leaked, we wouldn't know about it. And because of that too, we also have no ability to detect the threats because they're happening outside of our network. So how could we know this? And here's what I love about presenting to financial institutions about this topic is that ordinarily this is a surprise for people, right? They may not necessarily know this, but financial institutions, generally speaking, do know this. And we know that because they are taking some means or some measures to protect against some aspects of the solution. But because of how they do it, I'm afraid that there are still vulnerabilities. And so that's the problem that we're dealing with today. Let me say, first of all, that if any of this information here on our vulnerabilities is new to you and you have questions, please go ahead and send us an email or send Ron an email and connect it to us. We can get to them later or afterwards. Now let's talk about our solution to this problem, right? For the first years of our company existence, we literally just explained the problem, but now we have a solution as well. And it's not that the solution that exists today is bad. It served a purpose, but if we think about when that solution was developed in the mid-90s, the internet was a very different place, right? In the mid-90s, the population of the internet was doubling every single year, right? So creating a system that was security first, and that security was created by these stored keys at the certificate authorities, made sense because most of the connections that were being made were being made by new entrants who were fundamentally anonymous to secure those connections for the first time. So they built a security-first solution. And what I mean by security first is if, for example, you're logging into your financial institution, the first thing you're going to do is go to the web page, for example. And you're going to want to look at the left side of the address bar and see that that little lock icon is there in order to ensure for yourself that this is a secure connection. And only then after you've established the security do you then enter your username and password. In other words, security first and then identity. So I said that that's the security first solution that was invented before. Our most sensitive communication today doesn't reflect the situation that existed back in the 90s. So whereas that solution made sense then, we believe that now our observation is that our most sensitive communication is shared between known parties. Certainly in the examples I gave earlier where we talked about depositors connecting to their banks, bank services connecting to other bank services, or bank employees connecting to their bank services, or partner institutions, all of those represent cases where we know who we mean to connect to. And so why not build a system that uses our knowledge of that identity to establish better security? And that's what our solution does. Okay, the first part of enabling this type of communication is to identify the endpoints. And the way that that works at a high level is we provision the endpoints into our trust environment. That provisioning is analogous to how you might pair your phone to your car, for example, so you can make hands-free calls while you're driving or stream music. And the second thing that we do is we say who is allowed to talk to whom. So in this example right here, we're going to say the sender is allowed to communicate with the receiver. The only other points I'll make about that right now is this communication, no communication in our network relies on stored keys or existing solutions, but we use something that is rotating crypto, similar to a double ratchet cryptography, if you're into the crypto side of things. Okay, once we have that relationship in place, we know who the endpoints are, then when a sender wants to send data to the receiver, the sender will call an encrypt call, essentially, which will cause behind the scenes key DNA to be downloaded to the sender's machine. That key DNA, loosely speaking, is just something that allows the software on that machine to create a cryptographic key. The cryptographic key is again used to encrypt the data, but here's where it changes. Immediately after encrypting that data, we wipe the key from memory. Why do we wipe it? Because we don't need it anymore. Why would you keep a key around that can just be stolen by a bad actor to compromise that data in flight? Okay, next thing that we do is the sender actually sends the data to the receiver. And we don't actually have anything, any control over that. You can send the data however you want to, because our solution is a control plane solution. And that's good, A, because it's less overhead, and B, because it's easier to implement because we're not changing how the data flows through your system. Okay, on the receiving end, the key DNA is then again downloaded by the receiver. It's used to create a cryptographic key. That key is used to decrypt the data, and again, it's wiped from memory. The key only existed for a few microseconds in most cases, I should say. The next message is going to be sent using an entirely different cryptographic key. And we call this more secure because if the bad actor does grab this data in flight, there is literally no key to compromise anywhere that would allow them to decrypt that data. But it isn't just that we're more secure. Certainly we have eliminated hundreds of single points of failure, and that is a lot more secure. But we're also verifying every sender and every receiver, the encryptor and the decryptor, essentially creating audit logs that allow us to verify that that data was delivered safely. And the flip side of that same coin then is not only can we audit or verify that the data has been delivered safely, but we can also detect threats to that data. Right? If an unauthorized endpoint attempts to gain access to that key DNA, that's going to leave a log in our system, and we're going to be able to alert on that. We'll talk a little bit more about that later. But there's an expression that says that you get what you measure, and we measure the security of the data in flight in a way that existing systems cannot. Okay, so how does this turn into financial use cases? And let me tell you, I can't mention names here, but let me tell you about how we've been working with some of our partners. So the first is in mobile banking. I described that earlier. If you're using a mobile application to connect to your account, you'll notice here that in this sample app, this is an actual app here, I can't show it to you, we're actually verifying that all of these transactions were sent securely. Okay, we do that simply by provisioning the user's phones, and then of course the servers at the bank, and only allowing these provisioned phones to connect to those servers and access that user's communication, essentially building a friction-free multi-factor authentication into the communication and creating auditably secured communication in the process. Secondly, for web users, we can do the same thing but right in the browser. Our technology can be used to support WASM, which is just a technical way of saying that we can provision our endpoint right inside the browser and secure the communication from the browser to those same servers. When it comes to multiple data centers, multiple clouds or services talking to each other, we have a variety of tools that can be used to integrate this auditably secure communication. And that is, we can provide API proxies that encapsulate those calls as they move from one server to another, for example, with REST or gRPC calls. Or we've actually integrated into OpenSSH, for example, as a cipher within the TLS protocol. So even though the application may not need to have to change at all, they can use, again, our auditably secure communication. And in doing the TLS integration as well, we also are able to support VPNs that are based upon the ciphers inside the OpenSSL library, because they're using the same type of cryptographic negotiation, and so can leverage our auditably secure communication. Finally, if you need to communicate with other organizations, you can certainly deploy your API proxies on the other side. Or if that organization is also a customer of ours, we can also support trusted communication between organizations, right? So there are a lot of different ways that banks and other financial institutions can protect the security of the data, whether it's coming from a customer, whether it's coming from an employee, or from within services within those data centers. Fundamentally, what this delivers is something that is ultra secure by removing all those single points of failure. We're creating audit records for every data transfer, and you can see some of that in these screenshots that I have here, where I'm pointing out the flagged events and showing integration that is API driven to really any SIEM or data lake that you want to use in your system. And what this enables too is automated response to these attempted attacks on the data as it's in flight. Fundamentally, what we are finding with our early adopters in these markets is they are choosing us and they're looking at us because we provide them with a competitive advantage. Security is an important thing for especially high net worth individuals as they think about, who am I going to bank with in order to because I need to do banking, and who will do the best job of protecting my data as I'm using them. And that's why we think that this is an important technology for you all to consider, and we'd be happy to talk to you afterwards. If you do have questions about it, I can leave David's email up on the board here, and we'll be happy to follow up with you after.